So maybe it's weird, maybe it's confusing, maybe it's cool, but if you were to shake a charged object, that's going to create this electromagnetic wave. The electromagnetic wave has electric fields vibrating in one direction, magnetic fields vibrating perpendicular to what the electric fields are doing, and then energy rippling across space perpendicular to both of those. If you've already learned in a math class, this is related to something called the cross product. And again, depending where you go next year, you'll circle back and talk about cross product and how this propagation of light is following a cross product. To help make sense of it, it's kind of like if we were to shake a charged object up and down, we get these electric field wobbles that are also up and down. It'd be like if we took out a slinky, and if we shook the end of the slinky up and down, then we'd get a vibration traveling down the slinky that's also up and down. Light would also have the magnetic field that's left-right, but if we just want to think about electric field, whichever way we shake our charged object, we get an electric field that's wobbling in that same sort of plane. So shake the charged particle up and down, we get an electric field up and down, and a magnetic that's sideways. But the electric field is always the same as what the charge is doing. Here's where it gets a little bit weird. Some light sources are exactly like that. They produce vibrations that are always in the exact same orientation. So let's imagine you had a slinky and you always shook the end of it up and down. If you always shook the end of the slinky up and down, you always get a wave that's up and down. If we always shake a charge the same direction, we always get an electric field that's always in the same direction, and the magnetic field by definition is always perpendicular to that. So if we could always shake our charged particle vertically, we're going to get an electric field that's always vertical and a magnetic field that's always horizontal. If we have a light source that's like that, maybe it's not vertical and horizontal, but always the same orientation. So the orientation of the electric field, whatever it is, isn't changing. The orientation of the magnetic field, whatever it isn't changing. That's what we call a polarized light source. But there's a whole bunch of light sources that, sorry, a whole bunch of light sources that aren't that straightforward. Imagine, sorry, I'm choking here. Imagine that you took your slinky and you stretched it out, but instead of shaking the end just up and down, you took the end and you just shook it in totally random two-dimensional motion. Sometimes up and down, sometimes left to right. You just shook it all over the place, kind of like a mad person. Our eyeballs wouldn't notice the difference if we're talking about light, because our eyeballs don't respond really to the orientation of these electromagnetic waves. They just figure out the frequency as color, the amplitude as brightness. So our eyeballs wouldn't tell a difference. But that light source that's random, we would call it unpolarized. It would be different, fundamentally different than a polarized light source, but it would look the same. Here, I've got a graphic that kind of explains it. This graphic, an old school incandescent light bulb, you might not even have any of those in your house anymore. Maybe look inside your oven. If you've got an oven light, they tend to be old school incandescents. Inside your fridge, maybe an old school incandescent, but probably LED now. When it gives off light, what this part of the graphic's trying to show is that the electric field is wobbling randomly, sometimes up and down, sometimes it's wobbling up and down, sometimes it's wobbling on a funny angle, sometimes it's going left to right. Associated with that, always perpendicular to that, would be a magnetic field, but this graphic just shows the electric field. Since a light bulb does that, we would say that the light bulb, is not polarized. Because it's the orientation of these waves seems to be kind of random. Our eyeball doesn't see polarization, so we would just see the light coming off the light bulb. But that's what non-polarized light, fundamentally what it would look like. If we took that non-polarized light and we spent it through a special filter, a polarizing filter, which a lot of sunglasses have, it eliminates all the orientations but one. So this particular graphic, if the orientation that it lets through is, say, vertical, then it only lets through the electromagnetic waves that have an electrical part that's vertical. There'd be an associated magnetic part that's sideways, but the graphic's just showing electric. If we have a randomly polarized light source, we can polarize the light by using a filter. When the light's random like this over here, we say that it is not polarized. But if we put it through a filter, then we can say that it is polarized. We've lined it up, we've gotten rid of the randomness. Some light sources just are polarized. Some LEDs, some computer displays just come out polarized. Back to this, the light that comes off our sun is not polarized. It's totally random. But when it reflects off something shiny like water or sometimes off a road, that reflected light tends to get polarized a little bit. So if we put the appropriate polarizing filters into sunglasses, we can remove that component of the reflected light, which basically eliminates the glare. So polarized sunglasses, what they're doing is they're eliminating the reflected sunlight so you don't see the glare off water or the ground or glass or whatever you happen to be looking at. More complicated, if you go into a 3D movie, they put a lens in front of your right eyeball that's a little bit different than the lens in front of your left eyeball. So that when the light from the movie screen bounces into your eyeball, the image to your right eyeball is slightly different than the image to your left eyeball. And one of the deep things that your brain does is when it's making images, it looks at those slight differences between what your left eye sees and what your right eye sees to construct 3D. So by being clever with how they film and project the images and then using polarizing filters, they can send a slightly different image to your brain from your right eyeball than what's going to your brain from your left eyeball. And your brain can put that together to see 3D even though you're looking at a 2D screen. This is all kind of weird. The good news is I just want you to read through this and hopefully it sinks in a little bit. There's no worksheet or check-in to go with this. This is literally just to introduce, to get you thinking about light as a wave. It's this weird electromagnetic, perpendicular to each other, but energy perpendicular to that. Our eyeballs don't see this phase thing, so it's not a huge deal. We don't really see polarized versus unpolarized. What our eyeballs do see, what's going to come up over and over again, is we see the frequency of light shows up as color, and the amplitude of the light, which is energy, shows up as the brightness of the light. That's kind of the wave model of light. I'm going to label that because later that's going to get confusing when we start talking about Unit 5, but we'll save Unit 5 for another day. That's all I wanted to cover in this note. Read it over, take a breather, and then we're going to push on with an application of interference called the double slit experiment.